Let's take a look at a couple other mean and standard deviation examples. So in this case, we're going to look at roulette. So an American roulette wheel has 38 slots. There are the numbers 0 and 00 in addition to the numbers 1 through 36. You may want to look up what a roulette table looks like just to get a sense of these types of problems. It might help. Anyway, the ball is equally likely to come to rest in any of those slots. So there are, again, 38 of them. The slot numbers are laid out on a board, and basically you place your bets on them, and there are rows set up, and I tried to emphasize, what those rows look like. So you've got 1, 2, 3 is in a row, 4, 5, 6, 7, 8, 9, those are different rows. And then 0 and 00 have their own little row, but you tend, I'm going to remove that as an option for this, like betting on that row, because it has different odds. So suppose someone places a $10 row bet. So on one of those rows, 1, 2, 3, 4, 5, 6, 7, 8, 9, which means that if any of those numbers comes up, they win. So if you place your bet on the 1, 2, 3 row and 2 comes up, great, you win. Or 3 comes up, great, you win. Or 1 comes up, great, you win. And you're going to win $120. So pretty good payoff on your bet from the looks of it. So for starters, let's come up with a probability model for the scenario. Of course, taking into account the $10 that the game costs you to play. So for starters, we can say, well, there is, basically a 3 in 38 chance that we win, That's because if I place a single row bet, again, I'll just kind of say, suppose we place it on that first row, 1, 2, 3. There are 3 numbers that could hit that I would win. There are 38 total numbers. So there is a probability of 3 out of 38 that I win, and there is going to be therefore a 35 out of 38. I don't need to go through and count those up. I can just do 1 minus 3 out of 38, or if there are 38 total outcomes, 3 of them are wins, the remaining 35 are losses. So here's our win, here's our lose. Okay, what's the outcome? Which is otherwise known as our payoff. So the times that we lose, again, we lose the $10 that it cost us to play the game. So we have -10 as our outcome. If we win, then we should get $120, And that's, I should mention that when you play your money, when you play your $10 and you win, you just get that $10 back. So you're not netting anything extra. So basically this 120 is okay, we're going to pay you 120 on top of just your bet that you're getting back. So your outcome is plus 120. You're netting 120. So that's our probability model. So then we say, okay, well, what's our expected value for the game and what's our standard deviation for the game? Now there's, with only 2 different types of outcomes, it's not that crazy to do the expected value by hand because you just do the probabilities times the outcome. So we could do something like 3 out of 38 times 120 plus 35 out of 38 times -10. And this would be the expected value, otherwise known as the mean for our probability model. We could do this by hand, but of course we have a template that's going to do this for us. Same thing with standard deviation. So I'm going to bring up our template, and again, this document is going to be available to you, so you can reference this document as needed. So we have in red here, here's the template if we're given the frequencies, here's the template if we're given probabilities, or if we found probabilities, which we did. So we're going to say, okay, my data points and probabilities, well, the data points are going to be 120 and -10. Those are the possible outcomes. The probability that those happen with are going to be 3 out of 38 for winning, and 35 out of 38 for losing. Now these are fractions, and we can kind of expand these things and say, okay, is there a better way to write those? So maybe you prefer to see them this way, If I go back to fraction, it lists these as 0 and 1. It's rounding to the nearest fraction. Actually, not entirely sure why it is doing that for me. We see that it's 3 out of 38 up here. Let's see. I think leaving it that way is fine. But sure, if we want to see it as a decimal, just to make sure we're not fooling ourselves, and of course we can increase the number of decimals too if we need to. Anyway, what you may want to do is delete these extra rows, because otherwise you're going to have some values calculated in here. So I'm going to delete those just to make sure that they're not actually being counted for. Here we see the sum of our probabilities. That should be 1. X times P, so it's just multiplying these together. And notice that's exactly what we did. So here was our X 120 times its probability, -10 times its probability, and then we're just going to add those two up. That's basically what we said to do when we did this thing by hand, right? The outcome times the probability, the outcome times the probability, and then add them together. Okay, so we end up getting 0.26315, blah, blah, blah. So in this case, let's see, so we want to say our expected value, our expected outcome is 0.263. Right, and this is measured in dollars because the -10 was $-10, the 120 was $120. So in this case, we expect to have something positive. Probably what this means is that the casino would have to recalibrate their bet here. Otherwise, we could think about, well, what if this payout, the $120? Again, the problems hopefully are a little bit clear about this, but it could also mean that the payout here is really supposed to be 110, accounting for the $10. Usually our expected value should be negative. In general, we expect to lose money. The casino expects to win money. We could always check that. We could say, well, what if I did change this to 110? Does my expectation become negative? And sure enough, it does. Right, so probably this is what the problem intended, but for the moment we'll just leave it as 120. We'll see what happens from here. Because this is all templated, right, we already have the distance of each data point from the mean, or expectation, squared, and then that value times its probability here. And so we get a standard deviation here of 35. Now, something might not be obvious, but once you get a hang of these things, it's going to be a little bit more interesting to see a mean this small and a standard deviation this large relative to that. The reason is you have one really small value of -10 and one really big value of 120. So you've got this huge spread in possible results that could come out of this problem. So it's not that crazy that we would have something like this where we have what seems like a huge standard deviation relative to the mean. So we've got 35.055. And standard deviation actually is also measured in dollars, same way that the expected value or the mean is measured. So we expect, in this case again, let's just assume we're talking about actually winning $120 with our $10 coming back. We expect to win a little bit over 26 cents, but there is a huge standard deviation, so sometimes I'm going to lose everything and sometimes I'll win quite a bit. If we do change that to 110, let's just double check those values just to be sure. Right, this is probably a more realistic scenario. This is a problem I took from the book, so maybe the wording could have been more clear. So the expectation is negative again, like we would expect. So I'm just going to put that in parentheses where we say, okay, really though, probably I'm expecting to lose about 53 cents for each row bet that I do. And standard deviation will probably be similar. Sure enough, it is 32.358, blah, blah, blah. Okay, so let's say 32.36, just to kind of keep it simple. So 32.36, again, if we're talking about the 110 instead of the 120.